Hey guys, and welcome back to another mole lesson. So today's topic is how can we use the mole to change back and forth through number of particles? So we know that there are 6.02. Oh, that's not my pencil. Go back. There we go. We know that there are 6.02 times 10 to the power 23 particles. Avogadro's number. In 1 mole of a substance, which means we can actually treat that like a conversion factor. 6.02 times 10 to the 23. Let's call it atoms, although really it could be particles, but atoms just fits better. In 1 mole. So now we have another conversion factor. 6.02 times 10 to the 23 atoms is a mole. So if we know how many moles of a substance there are, well, it's pretty easy to figure out how many particles there are, right? If I have 1 mole of hydrogen, well, that's not an H at all. 1 mole of hydrogen. If I need to get rid of moles and go into particles, or in this case, atoms, well, my conversion factor is just 6.02 times 10 to the 23. So all I have to do is multiply. What is 1 times 6.2? Oh, well, this makes sense. This is the definition of a mole, right? 1 mole of hydrogen is 6.02 times 10 to the 23 hydrogen atoms. That is literally the definition of the mole, so that makes sense. But what if we had something harder? How many molecules, or how many moles, if I have 1.51 times 10 to the 24 molecules of methane? All right. So how can I use Avogadro? Well, I need to get rid of particles, right? So I need molecules on the bottom. And what am I changing into? Well, I need to get into moles. And what is my relationship between moles and molecules? 1 mole is 6.02 times 10 to the power 23 molecules. Awesome. Now, setting it up shouldn't be too hard with all the practice we've had. Solving it now can be a bit tricky. And I want you guys all now to pull out your calculators, pause the video, and try to find this answer. Because getting scientific notation in twice can be a little tricky. So I'll give you a minute here. Go for it. All right, that should have been lots of time for you to pause the video and give it a shot. So I'm going to tell you what I type into my calculator, and hopefully you can follow along and see if your answer doesn't match. So I'm typing in 1.51 times 10. I hit the power of button, 24 equals. I want to see that number on my calculator. It says 1.51 times 10 to the 24. Sometimes it might say E24 on your calculator. Now, I have to divide by, and I'm going to open a bracket. 6.02 times 10 to the power 23. Close the bracket. I should see Avogadro's number on my calculator. Then I hit equals. 2.508, on and on and on. Moles. Is it moles? Yes, it's moles, because molecules on the top, molecules on the bottom cancel out, and all that is left are moles. So make sure you can get 2.508 in your calculator. The biggest trick when doing multiple things with scientific notation, hit equals after you do the first one, and then put the second one in brackets. That works for my calculator. Of course, everyone's calculator is a little different, so find your actual calculator. Don't use your phone for this. Use the calculator you're going to use in class so you know how it works. Practice it until you can get this number every time. Moving on. How many particles are in 2.40 times 10 to the negative 5 moles of H2O? All right. I got to get out of moles. I got to get into particles. So I put the moles on the bottom because I have moles on the top over here. Those will cancel out. And what's my relationship? 1 mole is Avogadro's number, 6.02 times 10 to the 23 particles. Very important. So again, one more chance. Pause your video now and try to solve this on your own and see if you can get it to work. Go. All right, that should be enough time. Hopefully you paused and now you're back. 2.40. Oh, 2.40 times 10 to the power negative 5 times 6.02 times 10 to the power 23. Now you'll notice I didn't put brackets in this time. Why would I not put brackets in? Well, it's all multiplied, so it doesn't actually matter what order the stuff happens in. I could have done 2.40 times 6.02 times 10 to the negative 5 times 10 to the 23. I could bounce all over this equation. It'll still work. If they're all multiplies, you can do them in any order. 2 times 4 times 1 is the same as 1 times 2 times 4. Anyway, I digress. 1.44 times 10 to the power 19. And what am I left with? Moles are gone. Particles. And what are they particles of? Water. For now, because we're working with single things, because we're just starting to learn our chemistry, we kind of know it's water. It's the only thing in the question. Later on, when you're looking at, for example, a balanced equation and working with multiple chemicals, it is important that you name whichever chemical you're working with each time so you know which one it applies to. All right, how many moles is 5.29 times 10 to the power 24 calcium ions? Or atoms, sorry. 5.29 times 10 to the 24. These are atoms. And these are calcium. All right, I got to get rid of atoms of calcium and turn it into moles. 1 mole is 6.02 times 10 to the 23, right? Let's solve that one. 5.29 times 10 to the power 24 equals, divided by, open my brackets, 6.02 times 10 to the power 23 equals, this is 8.7, let's call it 8.79 moles of calcium. Now, what if I change the element? Instead of calcium, what if I have the same number, 5.29 times 10 to the 24 atoms, but instead of calcium, now I have aluminum. Think about it for a second. How many moles of aluminum will I have? Is it going to change or not? Let's take a look at how we convert this, right? I need to get rid of atoms of aluminum. I need to go into moles. Does the number of atoms per mole change ever? Well, it doesn't. 1 mole is always 6.02 times 10 to the 23. So these will be the same math. It'll be the same number of moles. So if you have the same number of particles, you have the same number of moles. That's what moles are. It's a measure of how many particles you have. So if I have 8 moles of aluminum, that's the same number of atoms as 8 moles of calcium, as 8 moles of hydrogen, as 8 moles of, I don't know, iron trichloride. No, that wouldn't make sense. Iron 3 chloride wouldn't be trichloride. It's ionic. You guys just did naming a little while ago. You should know this. So yeah, that's what moles is. It tells you how many particles you got. So moles are our universal currency in chemistry. Whenever you need to convert between anything, you're always going into moles first. So for example, how many particles are in 6.8 grams? I've got 6.8 grams. How the heck do I get to particles? I don't have a conversion factor that does, let's just call it atoms instead of particles. Atoms per gram does not exist. I do not have an atoms per gram conversion factor. So what I need first is moles. Moles is always, 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 circle this, square it, highlight it, underline it. Do not ever forget this. If you don't know what to do, turn it into moles every single time. You can always get into moles, and it's your universal currency. So I'm going to go to moles first. So I need to get rid of grams. I need to get into moles. What number relates moles and grams? Oh, that's molar mass, right? I've got carbon dioxide. I'm going to need the molar mass of carbon dioxide. So I've got 1 carbon, which weighs 12.011. And I've got oxygens. And I got 2 of them. Let me grab that calculator really quick. 15.999 times 2 plus 12.011. Molar mass of carbon dioxide is 44.009 grams per mole. And look, this is moles per gram. So this tells me that 1 mole should weigh 44.009 grams. Now that turns me into moles. Can I change moles into particles? Of course I can. There is a moles into particles conversion factor. 1 mole is Avogadro's number. 6.02 times 10 to the 23. That's why this number is so fundamental. It allows us to convert between whatever we want. So now I've canceled grams. I've canceled moles. So I'm going to take 6.8, divide it by 44.009, and then times that by 6.02 times 10 to the power of 23. Should get myself a real big number because I'm looking at number of atoms. Number of atoms should be big, or I guess molecules in this case. So you guys give it a shot. Pause the video here. All right, hopefully you had time to give it a shot there. I got 9.3017 something times 10 to the 22. I'll call it molecules because there's more than one. It's not an atom, it's a bunch of atoms together, so it's a molecule. 9.3 times 10 to the 22 molecules of carbon dioxide. So if you're ever stuck on what to do, moles first. Always. It is the universal currency. You can change anything into moles and moles into anything. You can even change from one, if you have a balanced equation, you can even convert from one element into another by looking at moles. Moles are crazy important to chemistry. Like literally from now on, pretty much everything you look at will have something to do with the mole. So make sure you got your head wrapped around that. Very important. You'll get lots of practice. How much does 9.03 times 10 to the 23 atoms of calcium weigh? What about aluminum? All right, let's try this out. 9.03 times 10 to the 23 atoms of calcium. Okay, how much does that weigh? Can I change atoms into weight? Do I have a conversion factor for atoms to weight? Well, no. So what do I got to do first? You should all be screaming at your monitors right now. Turn it into moles. Moles is always the universal thing. So I want to get rid of atoms. And I want to get into moles. Of course, it's Avogadro's number. 6.02 times 10 to the 23 atoms is 1 mole. And now I can get into weight. All I need is the molar mass of calcium, which I can look up in my periodic table. Calcium is 40.078 grams in a mole. Let's just double check. Atoms on the top, atoms on the bottom. Moles on the top, moles on the bottom. What's the only thing I haven't canceled? Grams? That means my answer should be in just grams. And what am I looking for? How much does it weigh? I'm looking for grams. Perfect. So let's punch this in. 9.03 times 10 to the power 23 divided by, in brackets, 6.02 times 10 to the power 23 equals times 40.078. Give it a shot before I answer it. Go for it. All right, so hopefully that went well. And you came out to 60.117. Call it 60.12 grams. So that many atoms is, well, we worked it out. It was 1.5 moles, right? If you're halfway through your calculation, if you stop to check, it was 1.5 moles. You times it by 40. Turns out you get 60 grams. All right. Now what if I had aluminum? 9.03 times 10 to the 23 atoms of aluminum. That's calcium. Well, change it into moles. 1 mole is 6.02 times 10 to times 10 to the 23 atoms. So if we go back one, before we finish this, back two, sorry. Same number of atoms gives me same number of moles, right? So should we get the same weight? Well, just because it's the same number of atoms doesn't mean it weighs the same. Not every atom has the same mass. So yes, we have the same number of moles. When I do this first step, this 9.03 times 10 to the 23, divided by 6.02 times 10 to the 23, I'll get the same number. I'll get 1.5 again. But the second step, I'm in atoms of aluminum. So how many grams of aluminum per mole means you have to look up aluminum's molar mass. So instead of having 40 on the top, I now have 26.982. So I punch that all in. Do my mole calculation, gives me 1.5 moles, times that by 26.982. So it turns out the same number of atoms of aluminum is only 40.47 grams. It weighs 20 grams less than calcium. It's, 2/3 of the weight of calcium. So even though it's the same number of atoms, one of them, calcium, is way heavier than the other. And this is because each atom has a different weight, and that weight is represented by your molar mass. So even though they're the same number of moles, 1 mole of carbon does not weigh the same as 1 mole of calcium, as 1 mole of aluminum, as 1 mole of iron. Every mole has a different mass because every atom has a different mass from other types of atoms. So all carbons would be the same, for example, but a carbon will always be different from something else, from an iron. So that is actually it for our mole unit, guys. We've covered all the major stuff. We've gone from moles to mass, and then from moles to particles, and finally, the trickiest part, from particles through moles back into masses. So this wraps it up. Here's everything we've covered from the very beginning. We talked about bond types. You have to know what an ionic bond is, metal plus non-metal. You have to know what a covalent is, non-metals, two metals, non-metals together. We talked about naming and writing ionic compounds. Right? You got to check your charges. And you got to do Roman numerals if there's a transition metal. Almost forgot how to spell numerals for a second there. That was embarrassing. Naming and writing covalent compounds, where you need the mono, di-tri prefixes. So if it's covalent, you use prefixes. We then spent a bit of time balancing chemical equations. Finally, we've wrapped up here with our beginning of the mole, looking at molar mass, converting between mass to moles, using molar mass. So first we figured out what molar mass was. Then we used molar mass as a conversion factor. Finally, we converted particles to moles using Avogadro. Oh, that's his name. I should probably capitalize it. 1 second. There it is. Very neat. Using Avogadro's number. And that's it. That's the whole unit. So spend some time reviewing this stuff. Make sure you've got a really firm grasp of it. Fire me an email or whatever you need if you have some questions, because we're going to have a unit test on this coming up soon. Thanks, guys, and have a great rest of your day.